Perfect. Cool, cool. Yeah, I don't think anyone will come.
Is anybody streaming right now?
7 people are, yeah.
Oh, nice.
Testing. Cool, cool, cool. I'm gonna try something different with the audio today. Is this microphone making noise when I tap it? Okay, I just wanted to see if the microphone was actually working. The audio quality on the live streams haven't been great, so I'm hoping that this. I wanted it to make noise tapping. How do I sound? Okay, can you guys hear me? Nice. Okay. Oh, I need water. I'll be back. You can keep it company until then. Audio and video quality should be much improved from last night. Got a new camera setup, so I don't know if you guys can see the improvement on your end, but much better from my perspective. This whole, I don't know, I can't get used to it.
I think it's weird. There's just like it's an empty lecture hall.
Yeah, I know.
Especially since you're so popular the first time. Nobody's here listening to you.
I know. Imagine this room would be packed under normal circumstances. That's kind of sad. Okay, we'll get started. Any remarks to begin with? I guess like before, I'm just going to start doing examples. If you guys have questions, you can use the chat feature. I'm going to check it regularly. So if you either don't understand something or you can't read something or you missed something I said, you can let me know. Otherwise, I will get going. Let's start off. I think I started off with an integral yesterday. I'll start off with an infinite series today. Just to get warmed up. So here's the question. Does the infinite sum from 1 to infinity of the square root of n squared plus 1 over n cubed plus n plus 7, does this converge or diverge? Okay, so as usual, given a question like this, the first kind of thing that I'm thinking about, I'll get over here. First kind of thing that I'm thinking about is, do I have a gut feeling for the behavior of the series? Usually I do, and usually when I have a gut feeling, it leads me in the correct direction to get a solution. So in particular, with something like this, I look at it and I think, what's the dominant behavior in the numerator? What's the dominant behavior in the denominator? In the numerator, let me write this down. In the numerator, under the square root, I have an n squared and I have a 1. In terms of infinite growth, the only thing that matters is the n squared. That's the most important thing. So in my mind, this is effectively square root of n squared. And then in the denominator, likewise, we have 3 different terms, the most important of which is the n cubed. So when I'm thinking about this infinite series in my head, I'm really just thinking of it as the square root of n squared over n cubed. And that's good because if I simplify this thing, this is an honest p-series, and I know exactly how it behaves. This is n over n cubed is 1n squared. Okay, so my intuition tells me that this infinite series should pretty much behave exactly the same as 1 over n squared. It's a p-series, I know it converges, so therefore I think that converges. And as usual, the way that I'll formalize this intuition is with a comparison test. Preferably limit comparison test, just because it's my favorite. So let me do limit comparison. How do I start off limit comparison? Limit comparison tells me to compute. So first, I'll say the limit as n goes to infinity. I take the thingy that we care about, which in this case is square root of n squared plus 1 over n cubed plus n plus 7. And then I want to divide all of that by 1 over n squared. And actually, I don't know if I've explicitly said this throughout the quarter, but when you do these limit comparison problems and you generate the thing to compare to, computationally, it's usually a better idea to keep it like this, actually, than to simplify it like this. It doesn't really matter. You'll get the same thing in the end, but I'll divide by the square root of n squared over n cubed. Okay. Now, I know that since I'm good with limit comparison, this limit's going to be 1. It's always going to work that way in standard limit comparison examples if you can pick the correct thing. Let's just justify that. So however you want to think about the algebra here is fine. The way I think about it is in the numerators, I've got a square root of n squared plus 1 divided by the square root of n squared. So I can collect those terms. And then in the denominators, I've got an n cubed blah, 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 blah divided by n cubed. So I can collect those. And then this kind of thing is, everything's going to simplify pretty nicely. Here, I can collect things under the square root. Underneath the square root, I've got n squared plus 1 over n squared. That'll be 1 plus 1 over n squared. That was maybe a couple steps of algebra on one. You can let me know if one of those is confusing. And then in the denominator, and then having written it like this, it's pretty easy to see that the numerator is going to 1. The denominator is also going to 1. So in total, the limit of this sequence is 1. That's good news for limit comparison because I don't have to worry about anything. If I get a limit of 1, I can always make a conclusion. So I'll finish it off by saying since 1 is a finite positive number, by limit comparison, that series that we care about behaves the same as the sum from 1 to infinity of 1 over n squared. Actually, maybe in my solution, since I started out with this, I'll write this. And then like I did over here, I'll simplify this to 1 over n squared. This one we know converges. The latter series is a convergent p-series. Sorry for squishing all of this in the bottom corner. I'll need to get better at using my limited board space. The latter series is a convergent p-series, so the former converges as well. So the former converges as well. It will, so the question is, could we ever get a negative number when we do something like limit comparison? The answer is no, because one of the assumptions for the limit comparison test is that both series are positive. So one thing to keep in mind when you run either direct comparison or limit comparison is that, strictly speaking, you're only allowed to do that with positive series. So the limit will always be positive or 0 or infinity. I did get a mic here. Yes, audio and video should be much improved over last night. Okay, now the one last remark I'll make about this kind of thing is, so tomorrow it's a 3-hour exam, and it's designed to be taken in 3 hours, but you have 24 hours. There's no excuse to not write out details, to not justify everything, to not write out a fleshed out answer. So you guys have seen me do a lot of limit comparison problems over the course of the quarter. They all look really similar to this. I usually write the same things. I say the same things. So if you can write all these things, you'll be in good shape. So is there a reason why we can't use non-positive series? There is. Well, so one answer to this is, let's say you have a series which is always negative. In that case, you could just factor out the negative sign, and you'll get negative times a positive series. And then you can just run comparison on the positive series. So really the scenario that breaks these comparison tests is if you have something which is both positive and negative. That's when things get a little iffy. But if you have something which is always negative, you can just pull out the negative sign, eject. Pull out the negative sign, and then you have a positive series. Cool. All right, moving on. Moving on. Oh, let's see. What do I want to do next? Let's evaluate an infinite series. So next up, here's the question. What is the value of the sum from n equals 0 to infinity of -1 to the n, pi to the 2n over 3 to the 2n factorial? Okay. So I get a question like this. I'm supposed to evaluate the series. Okay, so yeah, Nacho's correct in that this case, in the example that I just erased, we could say that that series converges absolutely, but it really doesn't have to do with limit comparison itself. It just boils down to the fact that if you take the absolute value of that series, you get the same thing. So that's correct. In that case, you could say that it converges absolutely. Okay. Now, anytime you get an infinite series that you have to evaluate, there's a couple standard options. If you're in Marco's class watching this, you have two options. One, it's either geometric, or you could use a Maclaurin series that you know. If you're not in Marco's class and you're watching this, another conceivable technique that you could use is a telescoping series. But for Marco people, don't worry about telescoping. We didn't talk about that stuff. So I look at this and I read, what is the value And that tells me that this is either geometric, because a geometric series I can evaluate, or it comes from a Maclaurin series that I should probably know. Well, it's for sure not geometric, right? There's a 2n factorial. So that rules out being geometric at all, which tells me this is probably the evaluation of a Maclaurin series that I know. So what I'm doing right now is I'm brainstorming, or I guess when I'm taking the test tomorrow, I'm opening up the book or the formula sheet to look at all these Maclaurin series that I know. And I'm asking myself, which one of those does this make me feel like? And it makes me feel like cosine. Now, we always have to be a little careful, but because I see a 2n factorial and a negative 1 to the n, I remember that the Maclaurin series for cosine looks a lot like this kind of thing. So in my solution, I would maybe start out by saying, recall that cosine of x, the Maclaurin series for this thing is the sum from 0 to infinity of negative 1 to the n, x to the 2n, over 2n factorial. And so then I just have to look at this and look at this really hard and figure out, is there an x value that I could stick in here to get this kind of thing? And it looks like if I were to group these two terms together into like one thing, I could write that as pi over 3 to the 2n. And then this would be cosine of pi over 3. Okay, so I would probably write it like starting with this series. That's the thing that we care about. Negative 1 to the n, pi to the 2n over 3 to the 2n, 2n factorial. This, if I collect these terms, this is the sum from 0 to infinity of negative 1 to the n over 2n factorial times pi over 3, all of this to the 2n. And then this matches up exactly with the Maclaurin series for cosine, so this tells me that this must be cosine of pi over 3. And we just have to remember the unit circle. Cosine of pi over 3, I think, is 1/2. And there we go. So this infinite series, first of all, converges. And it converges to 1/2. Nice. Okay. So anyway, I think the takeaway from this problem is, at least if you're in Marco's class and you have to evaluate an infinite series, in other words, if you have to give the exact value of an infinite series, it's either going to be a geometric series or it'll be a Maclaurin series. Rather, it will come from a Maclaurin series. Cool. Okay, I'm feeling an integral next. Let's do an improper integral as well, just to make sure we cover one of those, since, like I said last night, I haven't talked about improper integrals in section yet. Whew. That's what I get for using a corded mic. All right. Try not to do that again. 20 minutes in and we've already had one mishap. Sorry about that. Okay. Nice. Next up, here's the question. Does the integral from 1 to infinity of x over 1 plus x squared quantity squared dx, does this converge or diverge? And then if it converges, tell me what it converges to. So does this converge or diverge? And if it converges, what does it equal? Okay. So what's the point? If I'm asked if an integral converges or diverges, that means the integral is improper, maybe. So we have to think about, why is this thing improper? I see an infinity here, so it's for sure improper for that reason. But then it's always a good question to ask, is the integral improper for any other reason? Because if it is, if you have an integral which is improper for multiple reasons, you have to split it up into multiple pieces. In this case, I don't think we have any other issues. The other kind of thing you want to be on the lookout for is, for example, if I divide by 0 at any point, that's not going to happen here because 1 plus x squared is always positive. So the only reason why this is okay. So what do? The way to deal with an improper integral is just to write it as a limit of proper integrals. So in practice, when you get an improper integral, you identify the trouble spot, which in our case is infinity, and you say, hold on, it doesn't make sense to integrate from 1 to infinity. So what if I just integrate from 1 to a really big number like r? So let me write that down. I will instead integrate from 1 to r of blah, 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 blah. And then I just need to take a limit as r goes to infinity. So tomorrow, if you get an improper integral, your first step is to just rewrite it as a limit based on the issue spot that you have. Now the point is, from here, these things right here are just regular old integrals that we can do with no problem. So the question would be, how do I evaluate such an integral? Think about it for a sec. So Mark asks, what other traits could an improper integral have? The other kind of thing that you want to watch out for is, for example, if I wrote 0 to 1 of 1 over x, this one is improper because of 0, roughly because you divide by 0. So the things you want to be on the lookout for are either a bound of infinity, or dividing by 0, or taking like log of 0, something like that. That would also be improper. That's the idea. All right, so we've got U sub ideas. That seems good to me. I identify a relatively straightforward composition of functions, which is the 1 plus x squared blah, blah, blah squared. I can see that if I substitute for that, my dx up to a constant will be up top. So if it were me, I would say, let u be 1 plus x squared. du in this case is 2x dx. I need to change everything, and the way I'm going to do this is I'm going to change the bounds also. So this will turn into the limit as r goes to infinity of, let's see, x dx is 1/2 du. So the factor of 1/2 I can pull out front, du. And then in the denominator, I have u squared. And then I change the bounds. When x is 1, u is 1 plus 1, so it's 2. And then when x is r, u is 1 plus r squared. I get that. Then, easy antiderivative, this is just the power rule. This is like u to the negative 2. So power rule says increase the power by 1, evaluate at the two bounds, which are 1 plus r squared and 2. Plug it in, and then we'll just have a limit to evaluate. So maybe let me keep the question up, and I'll continue over here. Solution continued. So let's see, when we plug in plug in 1 plus r squared, we'll get a negative 1 over 1 plus r squared, and then minus negative 1 over 2, so that should be plus 1 over 2. I think I did that correctly. Probably. And then we can take the limit. As r goes to infinity, what happens to this term here? Denominators get really, really, really big. So this fraction goes to 0. And so in total, we're left with 1/2 times 1/2, which is a fourth. And then we're done. This tells us two things. One, since 1/4 is a finite number, it tells us that the integral converged. And by doing this process, we've actually shown that the integral converges to 1/4. In other words, it equals 1/4. So the integral converges to 1/4. Done. All right. Another one down. We're flying. Get an example with both infinity and zeros bounds. Yes, that could definitely happen. And so, yeah, if you want to check out, I think I did an example from yesterday's. The video's online, and I think I have links in the description. So if you want, you can go check out that one. Roughly, the idea is what Ian said is correct, is that you'd want to split that up somewhere, like, for example, at 1, and then break it up into 2. Now, you know, just because one of the bounds is 0 doesn't mean it's improper. Nothing changes. 0 is fine here. If I plug in 0, nothing bad happens. So even if I started this one at 0, the only reason why this would be improper is still because of the infinity. But yeah, good question. Cool. So the 1 plus r squared came from here. Every time you do a u substitution, whether you like it or not, you are supposed to change the bounds. So in other words, up here, when I write these bounds, this is implicitly telling me that x is r. But then when I go down here, I'm writing things in terms of u. So I have to figure out what my upper bound is in terms of u. So this number came from saying when x is r, what is u? U is just 1 plus r squared. And then the 2 came from plugging in 1 for x. Sweet. All right. Okay. Next, I want to do kind of a long involved problem involving a Maclaurin series, and it'll put together quite a few concepts from chapter 11 into one problem. So buckle up. Let's do this. Okay, the one bad thing about live streaming these is I don't really have much board space. So I might write a little small. If you guys can't see anything, you can just let me know. So here's the next example. This will be a multi-parter. But to me, it's one of the most interesting things about 31B at all. And it gets to the heart of why we study these things. And for example, it gets to the heart of like, what good is a Taylor series or what good is a Maclaurin series? Like, what's the point there? Yeah, that would be fine. As long as you do change them to asterisks. Like so the one thing that you shouldn't do, the wrong thing to do would just be to write this as R and this as 1. If you write 1 to R here, that is incorrect. But if you acknowledge that the bounds change, that's probably fine too. Or yesterday in the review session when I did improper integrals, I think I did a couple examples where I isolated the antiderivative, and I just did the antiderivative as a separate problem, and then I plugged back in. But yeah, that's probably fine. All right, so part A, find the Maclaurin series of t cubed dt. That's part A. Part B, convert the integral from 0 to 1 of sine of t cubed into an infinite sum. And then one last part, C, use the second partial sum of your series from part B to estimate the value of the integral. And then furthermore, estimate how accurate your estimate is. Okay, so that's kind of a lot, and it might be a little overwhelming to look at, but we'll take it piece by piece, and I'll explain everything. So if you read that and you're like, oh my God, Joe, I have no clue what you're talking about, don't worry about it. It's a multi-part problem, so you just take a multi-part problem step by step. Okay. I need to remember to only turn this way. Also, like I said, if I'm writing too small, let me know, but I think it looks fine to me. The bounds in part A are 0 to x. So the upper bound is a variable x. Yeah. Okay, so part A, we have to find a Maclaurin series for a ridiculous looking function defined as an integral. How do we do that? So I mentioned this yesterday a couple times, but one thing to keep in mind is that on a test or in life or whatever, if you're asked to compute a Maclaurin series, probably the way that you're going to do that is you'll use a Maclaurin series that you already know. Rather than use the general formula, you can probably take a shortcut. And in this question, I look at this expression, and I latch on to the sine, and I think, I already know the Maclaurin series for sine, so maybe I can use that to my advantage. So that's how I'll start, is I'll say, recall that sine of something, sine of star, the Maclaurin series for this thing is the sum from 0 to infinity of -1 to the n, star to the 2n plus 1 over 2n plus 1 factorial. Okay. And this is what I'll base all of these computations off of. So let's start here. And we ultimately want to figure out this expression, the integral from 0 to x of sine of t cubed dt. Well, this is just the integral from 0 to x of sine of t cubed. So I'll take the Maclaurin series expression here, and everywhere I see a star, I just plug in t cubed. That would give me -1 to the n times t cubed to the 2n plus 1 all over 2n plus 1 factorial dt. This looks insane to me. It looks really scary, and you just have to keep everything straight and realize that it's not that, it's a little scary, but it's not that scary. This is just a polynomial, right? Sigma, blah, 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 that's just a fancy way to write an infinitely long polynomial. So all this is the integral of a polynomial. Okay. Now, the one thing that's always good to do in these problems when you have something like this is to simplify the powers of your variable as much as possible. So let me do that in the next step. -1 to the n over 2n plus 1 factorial. Here, t cubed to the 2n plus 1. This is the same thing as t to the 3 times 2n plus 1, which is like 6n plus 3, I think, dt. And we get that. Then, what's the point of these questions? We're integrating a power series. How do you integrate a power series? You just integrate each term individually. The next observation is the dt here, which is really important. It's telling us that the variable we're integrating with respect to is t. So everything that isn't a t is constant with respect to t, obviously. And the only reason I stress that is because what can we do with constants in integrals? You can pull them through the integral sign. So here, what I'm going to do, I'll give myself some more room. I have this integral sign, and I'm going to pull all of this stuff through the integral. I can't pull the t because it's a t, but so then I'm left with the integral from 0 to x of t to the 6n plus 3 dt. Okay. Now, having done that, again, it looks scary still, but this thing right here is just integrating a power of t. That's very straightforward to do. That's just the power rule. Power rule would say increase the power of t by 1, divide by the new power, and then evaluate at the two bounds, x and 0. And then maybe I'll squish this last step down in here. when we plug in t equals 0, this expression right here is 0 to the whatever, which is 0. So when I plug in 0, everything dies. It's all 0. Up here, when you plug in x, the t just turns into an x, and so in the end, what we're left with is the sum from 0 to infinity of -1 to the n over 2n plus 1 factorial times 6n plus 4. All of that times x to the 6n plus 4. Looks a little ridiculous, but that expression there, that'd be the Maclaurin series for this function in part A. So the summation sign didn't go away. It's still there. If you're talking about from here the integral sign over the sigma, I don't know if that helps at all, but the way to think about this is if I gave us the integral of 1 plus x, well, this is just the integral of 1 plus the integral of x. In other words, the integral of a sum is just the sum of the integrals. That's what's happening in that step. I don't know if that makes sense. But the summation didn't disappear. It's definitely still there. I just moved it through the integral. Whew, okay, that was part A. I don't think so. Yeah, I don't know why we'd have a negative sign in front unless I screwed up somewhere, but I think we're in good shape. As far as Maclaurin series, you should know, they're all on the formula sheet. So you'll have the formula sheet, and I wouldn't worry about memorizing any of them. I mean, I don't think it's a bad idea to have like e to the x, sine of x, cosine of x, and 1 over 1 minus x memorized, but you'll get a formula sheet, so I wouldn't worry about that. Okay. Think I'm okay? Here's the Maclaurin series. Now, what's part B? Part B says convert the integral from 0 to 1 into an infinite sum. That sounds kind of impressive, but we've done all the hard work. This expression right here is the integral from 0 to x. So if I want the sum from 0 to 1, or sorry, if I want the integral from 0 to 1, all we have to do is just plug in 1 for x, and that's it. So part B, the integral from 0 to 1 of sine of t cubed is, well, that right there is the integral from 0 to x. So all we need to do is just plug in x equals 1. Sorry. When we do that, 1 to the 6n plus 4 is just 1. So that part goes away. And we're left with -1 to the n all over 2n plus 1 factorial times 6n plus 4. Done. I think this alone is like really cool. I love this stuff so much. Yeah. So, Oh, thanks, Cheney. That may have been what Jonathan was asking about. Yeah, since you plug in x and then minus 0, the term with the 0 goes away, but the term with the x, which had a positive in front of it, stays. Yes, so part B, when you first read the question, sounds really scary and impressive, but having done part A, literally all we did is I just plugged in x equals 1 into whatever expression I got for part A. That's exactly right. And like I said, I think this is really cool. But the even cooler part is in part C. So what does part C say? Use S2 of your series from part B to estimate the value of this integral. Like I said, this is getting to the point at why all of this nonsense math that we're doing is useful at all, or like what's the point of it? That integral that I wrote here, I could be wrong, but 0 to 1 of sine of t cubed, integrating sine of t cubed is really hard, maybe impossible. I don't think I could do it. If you want, one of you guys can plug it into Wolfram Alpha to see if it spits out an answer. But the point of this is like integrating sine of t cubed by hand, you probably can't do it. So what if you care about the integral from 0 to 1 of sine of t cubed? What do? We've just converted it into an infinite sum, a sum of infinite numbers, and we can approximate the value of that sum by just taking the first few terms. And that'll give us an approximation for this integral. In particular, part C is telling us to use S2 to do that. So in part C, we have to remember, what does S sub 2 mean? That always means the second partial sum. So in other words, instead of adding off to infinity, I just add up to 2. So S2 would be the sum from 0 to infinity of this stuff. Nope, 0 to 2, sorry about that. Uh, 6n plus 4. Which is what? So let's just write that out. When n equals 0, what do I get here? I'll get 1. 1 factorial is 1, and then a fourth. That's the n equals 0 term. Oh, so the x equals 1 just comes from, look at these two things right here. In part A, this is what we found. And this is what we want in part B. They're the exact same. The only difference is that x equals 1. That's it. So the n equals 0 term is a fourth. The n equals 1 term would be minus 1 over 3 factorial times 10. I think. And then the n equals 2 term would be plus 1 over 5 factorial times 12 plus 4 is 16. Okay. So whatever that fraction is, if we wanted to, we could simplify it. But the idea is that that's an approximation for this impossible integral that we don't know how to do. Okay. But that wasn't all that part C asked. Part C wants us to estimate how accurate this is. No. in part, so I don't know how much of this is confusing or not, but in part B, it's 0 to 1 just because I wanted it to be. Just because I wrote the question, so I made it 0 to 1. There's no good reason why that's the case. I could have asked for 0 to 2. I could have asked for 0 to a billion, etc. So you can roughly think about series as kind of a discrete approximation to integrals. It depends on how you interpret things. You know, for example, like here, the series is literally the integral, but then if you want to think about Riemann sums or something like that, yeah, you could think about series as being kind of a discrete analog in some vague metaphorical sense for a series. Anyway, this alone is pretty cool. We have an approximation for this integral, but then I asked something more, which is estimate the accuracy. In other words, I want to know how close this number is to the true value of this integral. How in the world do we do that? And also, I'll say that if Marco gives you a question like this tomorrow, he'll probably hold your hand a little bit more. Like, he'll explain what he's looking for, because it might be a little hard otherwise. But like I said, to me, this is really the point of all of this. So the question is, how in the world could we determine how accurate this is? What kind of series is this? It's an alternating series. And we have this annoying theorem, the S minus Sn less than Bn plus 1. That's exactly what that tells us, is it gives us an estimate for how accurate the partial sums of the infinite series are. So the point of the last part of part C is that this is an alternating series. And the thing to recall, and like I said, Marco would probably tell you to use this if he wanted you to, but recall that if we have an alternate series written like this, which converges to S, then the alternating series estimate thing says that the difference between S and Sn is less than Bn plus 1. That's the fact that we're going to use here. So what we care about is S2. So we know that the difference between the true value S, which is this integral here, is less than B3, which is what? Bn, in our case here, if I look at this alternating series, Bn would be everything except for the -1 to the n. So this is like 1 over 2n plus 1 factorial times 6n plus 4. So B3 is going to be 1 over 7 factorial times, 18 plus 4 is 22. Okay. And we're done, but just because this is cool, give me a second. 7 factorial times 22 is 110,000 and change. So this number is less than 1 over 100,000. This is so cool. So this integral is impossible to do. You can't do it. I can't do it. No one can do it. we just computed the true value of that integral to an accuracy of like 6 decimal places by hand. Did not once touch a computer. That's like a chalk drop moment. That's so cool to me. And this, like I said, this is the point of like all of this. This is a really good example for why all of this stuff is useful. Anyway, I'll stop gushing over this. So the intuition behind this thing, roughly, so we've used this a lot and it's really confusing. All it's saying is that if you have an alternating series and it converges, if you have an alternating series which converges by the alternating series test, then what do the partial sums look like? You add something, then you subtract, then you add, then you subtract, then you add, then you subtract. And so you just go like this forever and ever. So let's say here's the true value. Because it's alternating, because you always add, then subtract, then add, then subtract, every time you add and subtract a term, you go over and then under, then over, then under, then over, then under, then over, then under. It has to work that way. So the idea is, let's say I do this a finite number of times, and I stop here, and I want to know how far away I am from here. Well, I know that the next term I add is going to put me over. What that tells me is that I'm closer than the next term I add. We're closer than the next term I add. That's what that's saying, roughly. All right. I'll do a Q&A once I hit 100 subscribers. Sounds good. Anyway, that's that problem. Like I said, and then we'll move on. The first time that you learn all this stuff, like infinite series and Maclaurin series, and it's like, what the hell is happening, and so confusing and intimidating. It really is cool. It takes a long time to see that, and it takes a long time to get everything. But once you do, to me, this is a great example of like why this stuff is so useful and why it's so cool that we just computed, I'll repeat that, we computed an impossible integral to like 6 decimal places without touching a calculator, a computer, or anything. That's really cool. Okay, moving on. Let's do something a little less cool now. Like, everything's cool in 31B, but a little less cool. Let's do another integral, but one that we can actually do. Okay. What I'd really love to do is a live stream of like titled "Why 31B is so cool," and then I would just do a bunch of cool stuff. I don't know if anyone would actually watch that, but maybe I'll make a video about that stuff because there's a whole lot of fun stuff. The integral of, let's do e to the 2x times sine of x. Ooh, I don't know about that. A Q&A during the test tomorrow? Probably not. Okay. So I get an integral like this, and I start thinking, what are my options? Can I do any obvious algebra? No, I don't think so. Can I do a simple substitution? I don't think so. I don't really see any compositions of functions that stand out. So then after I rule out those two possibilities, I start thinking about my chapter 8 techniques. Chapter 8 techniques that we've learned are integration by parts, partial fractions, and trig stuff. Suze says integration by parts. I agree. One, it's a product of things, so I don't know. That's usually good for integration by parts. It's definitely not partial fractions, and because there's an e to the 2x, it's not going to be like a trig type thing. Also, if you've done your homework or if you've done a bunch of practice problems, you've probably done something like this. And that's what you do in math, is you fall back on experience. So I think the answer is no. I'm gonna go missing tomorrow in terms of 31B. Unfortunately, I don't think you're allowed to seek me out for help. Sorry. So let's try integrating by parts. Now, the one goofy thing about this kind of example is, well, also let me remind us what the integration by parts formula says. It says the integral of u dv is uv minus v du. So as usual, given something like this, we have to decide what we're going to call u and what we're going to call dv. Oftentimes, there's kind of a right answer. I mean, and you can always do whatever you want, but usually there's something that you can do that will be the most helpful. This is a scenario where you could do either. You could pick either e to the 2x to be u, or you could pick sine of x to be u. They'll both work in the end. For this specific problem, I'm more tempted to call e to the 2x u, just because if I were to call dv e to the 2x, when I integrate that to get v, I'm going to have to divide by 2, and then I'll start picking up fractions, and fractions are hard. I don't want to think about fractions. Whereas if I were to call u e to the 2x, when I differentiate that, I'll just be multiplying by 2. And that might be a little easier to deal with, but either would work. So I would probably call u e to the 2x. dv is going to be sine of x dx. But maybe I'll say either, in this case, could do opposite. And if you don't believe me, try it, and we should get the same answer in the end. Okay. So then du is going to be the derivative of this. This will be 2e to the 2x dx. And then v, okay, I have to think now. If dv is sine of x, the antiderivative of that should be negative cosine. So then let me run this formula and see what we get. Antiderivative of blah, 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 blah that we care about is u times v. So that'll be a negative e to the 2x times cosine of x minus the integral of v. V's got a negative sign, so I can pull that out front. Du has a 2 here, so I can pull that out front, and then I'm left with e to the 2x cosine of x. Okay. That's one application of integration by parts. So I get here, and then as usual, integrating by parts doesn't ever give you the answer, it just transforms the integral into something new. So we look at this and we ask, now what? gee, that looks a whole lot like the thing we started with, and we decided that that was an integration by parts problem. So I think we should integrate by parts again. Make a TikTok at 200 subscribers. Maybe. That would really, really help me go viral if I tapped into the TikTok community. I'm sure math is like a pretty big thing on TikTok, if I had to guess. Maybe not. All right, so I get here. I want to integrate by parts again. Now, unlike in the green over there, I said you could do either. Now there is a correct answer. Now there's only one thing you can do. You want to be consistent with your first integration by parts. So in other words, because in the first step I called u e to the 2x, I want to do that again. U is going to be e to the 2x, and dv will be cosine of x. So at this step, you cannot, I mean, you can, but you should not. Don't switch choices here. Because if you do, you'll just unravel everything that you did in the first step, and that would not be good. So let's try this, see what happens. Du is going to be, again, 2e to the 2x. And then v is sine of x. Okay. So I run integration by parts again, and I hit this thing. So let me write all this out. This will be kind of annoying. The integral of e to the 2x sine of x dx is negative e to the 2x cosine of x plus 2 times, and then this thing in the square brackets, I'm hitting with integration by parts again. So I'll get over here u times v. So this will be e to the 2x sine of x minus the integral of v du. Du has, whoops, du has a 2 that I can pull out front. And then v du, that will give me e to the 2x sine of x dx. Close the square brackets. Okay. Okay, so that's a fair question. Like, is it naughty for me to reuse u and v? In this case, I don't think so. It would be different if I did a substitution where I called like u equals this, and then I did some stuff. I probably wouldn't want to reuse u there. But I guess the way that I think about this kind of solution is that integrating by parts is like its own environment. So like I have the integral, and then I decide, okay, I want to integrate by parts. So then I enter this like bubble environment of integrating by parts. I call u and dv stuff in here, and then I do my thing, and then I get out something. And then I want to integrate by parts again. Well, that u and dv, they were in their own environment. So to me, I don't think it's an issue. But if you want to, you could use a and b. You could use smiley face and frowny face or something like that. Actually, probably don't do that. But okay. Now, just have to be careful about this 2. I want to distribute it. Two e to the 2x sine of x. And then minus, I've got a 2 times 2 is 4. And then we say, damn it, we're back where we started. We didn't do anything. Fortunately, this is the point of this example. is that's exactly what we want to happen. We want to get back the original integral that we started with because, so why did I use square brackets? I don't know. I was feeling square, but there's no reason to do it. You could use regular ones if you want. Sometimes I'm in the mood for square brackets. And then, yeah, that's kind of what I was talking about, is that if you do like 2 substitutions in a row, I would definitely use different letters. Because in case you need to like back substitute, you'll get really confused if you reuse a letter. So yeah, that's exactly what I was talking about. Okay. So I get this equation, and it looks kind of hopeless, but the idea is that here I have something that I care about. So let me call that smiley face. And here I have something that I care about. It's the exact same thing. So the point is, now we can just treat this like an algebraic equation, just like we were back in high school, and solve for the unknown, solve for smiley face. How would I do that? I've got blah, blah, blah equals some stuff minus 4 times blah, 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 blah. I would probably add this term over here, which would give me 5 times smiley face equals this stuff. So let me finish that off here. This will be kind of annoying. Okay, so the integral of e to the 2x sine of x, which was the thing that we cared about, is 1/5 when I divide by 5 times this stuff. Sorry for squishing this in the corner. Plus c, and that would do it. Okay. So integration by parts, but one of the tricky things that can happen in integration by parts problems is you sometimes start with something, and then you do a whole bunch of work, and then you end up with the thing that you started with. And that's not necessarily bad. You might be able to just relate it back to itself and algebraically solve. This is exactly the kind of thing that happens when you prove a reduction formula for like sine or cosine or something like that. All right. Moving on, moving on. Let's do another infinite sum. Excuse me. Okay, next up, does the sum from 1 to infinity of log of n okay. I'll let you think for a couple seconds. I'll sit down for like 10 seconds. Oh, or you can see my head, so I'll think out loud. So I look at this, and I'm running through my options. And if anyone has ideas, you can let me know. But the thing that stands out to me is okay, so in this problem, if you had done the opposite, and I encourage you to try if you want so that you can see this for yourself. But over here, if we had called u cosine of x and dv e to the 2x, you'd run the integration by parts, and what would happen is you would, after simplified, you would get the equation 0 equals 0. And that's true, but not helpful. Okay, so some good thoughts. I like Nacho's thoughts. The intuition says, you know, like, do I think it converges or diverges? You guys are saying the correct stuff, which is that 2 to the n grows a lot faster than log of n. So therefore, it suggests that it would converge. I agree. Now, how do we show that? I like the ratio test. That's what I'm going to do. And the thing to keep in mind is that there's kind of two indications. Sorry, I'm getting the hiccups. There's two indications, or there's a couple major indications for when the ratio test is really useful. One of them is if you see a factorial. That's like an immediate, don't think about anything else, just do the ratio test. The other less common thing that tells you that the ratio test is a good idea is if you have exponential looking things together with other stuff, roughly. Actually, in general, if you just have exponential looking things, the ratio test is usually a good idea. So Nacho identified, oh, there's a 2 to the n in the denominator. I could use the ratio test. So yeah, I agree. Let's try it. All right, so the ratio test would say, compute the limit of, in absolute value, the n plus first term here would be log of n plus 1 over 2 to the n plus 1. And then divide that by the nth term, which is the same thing as multiplying by the reciprocal of that. So this would be 2 to the n over log of n. And that's the limit we need to compute. Oh. So continuing up here, as usual with the ratio test, you want to simplify exponential or factorial looking things, and then anything that's not exponential or factorial, just scoot it to the side and don't worry about it. So everything's positive here, so I can drop the absolute values. A 2 to the n over 2 to the n plus 1. That leaves one copy of 2 in the bottom. And then, like I said, the things that didn't come from exponentials, I'll just group to the side and let them hang out. Because usually, you won't be able to simplify them in any meaningful way. Okay. And we have to figure out what this limit is. This part's going to go to 1. For practice, we could just show that. You know, like I said, you'll have a long time tomorrow to work on the test, so if there's little details you can justify, may as well. So if it were me and I wanted to be like an A triple plus student, I would recognize that I'm going to use L'Hopital here. I'd switch to X. This is infinity over infinity indeterminate form, so L'Hopital's rule would say that this is the limit as x goes to infinity of the derivative here over the derivative here and then this simplifies when I divide this denominator by x. This will be like 1 over 1 plus 1 over x. This term goes to 1, so then I get 1/2. 1/2 is less than 1, so by the ratio test, this converges. Done. Okay. So that's maybe a relatively straightforward ratio test problem, but good to do nonetheless. Also, I've talked about these kind of things a lot, but I'll just point them out again. So could we also do direct comparison? Maybe. I don't know with what. That would be the thing to be careful about. I think, so we could think about that. Comparing with 1/2 to the n would not work because that thing is bigger. So you'd have to do something else. Really, if you wanted to run a comparison argument, you could probably do something like point k. It would work, but you'd get an endpoint case, and it's kind of an odd-looking solution. But you could do like limit comparison with something like 1/n², for example, or you could do a couple things. But probably the most straightforward solution is this ratio testing. What was I going to say? I was going to say something, but I forget. So I'll move on. Okay, another one down. Oh, I know what I want to do next. Okay, next, I want to evaluate arc sine of sine of 5π/7. Okay. What's the point of a question like this? The point of a question like this is that arc sine of sine, they don't necessarily just cancel each other out. Even though arc sine is the inverse of sine of x, it's the inverse of sine of x on a restricted domain. And this makes a π/7. It doesn't necessarily work like that. Why? Verbally, and I can write this down if you guys want, but when we talk about arc sine, we restrict the domain to -π/2 to π/2, which means the range of arc sine is -π/2 to π/2. And 5π/7 is bigger, I think, than π/2. So it's definitely not this. Okay, so what is it? What we have to figure out is arc sine, so I'll say this out loud and it won't make sense, and then I'll draw the picture, which is actually how I think about this kind of thing. Arc sine of 5 pi over 7, that is the thing that you feed to sine on the interval negative pi over 2 to pi over 2 to get sine of 5 pi over 7. That's not helpful at all. Here's the picture. And this is what you should be thinking about in a problem like this. So here's my attempt at drawing a unit circle. That was pretty good. The right-hand side is good. The left-hand side is a little stunted. That's okay. Like I said, the range of arc sine is negative pi over 2 to pi over 2, which means the angles that we care about in terms of this problem are over here. That's the good range. I don't know if you guys can see the green. Yeah, a little bit. Okay. The angle that I'm feeding in here is 5 pi over 7, which, so here's pi. So 5/7 pi is, I don't know, something like that. Height here, right? So this height right here is sine of 5 pi over 7. And what we're trying to do when we evaluate this expression is figure out what angle do I put in over here to get out the same height. In other words, what angle over here gives me the same sine value? Since I've drawn the picture, we can just see what it is. Geometrically, that angle that I care about is this. In this specific case, it's like the reflection of this angle. So whatever star is, that's the value of this expression. That's all we have to figure out. And because it's symmetric, by symmetry, star is going to be whatever this angle is. And if this was 5 pi over 7, and this is pi, which is like 7 pi over 7, that tells me that this angle right here is 2 pi over 7. So that's what star should be. All right, so picture proof shows that arc sine of 5 pi over 7 is 2 pi over 7. Whew, done. Nice. Evaluating inverse trig stuff can be tricky just because of all these domain restrictions. So there's a lot going on there. All right, let's do all right, let's do this. Oh, I'm already at 100 subscribers. Nice. What was I going to do at 100 subscribers? Oh, Q&A. All right. You guys can ask me any question, and I may or may not answer. So the circle comes from sine of 5 pi over 7. When we talk about sine of an angle, that always gives us the height. Sine is the y value. So the height here at angle 5 pi over 7 is whatever this is. I don't know what that is. Like I literally don't know what sine of 5 pi over 7 is, but whatever it is, it'll be that height. But to arc sine that, arc sine spits out an angle over here. So arc sine of this height it's going to be the angle over here, which gives me this height. And that's exactly whatever that angle is right there. So then you just have to figure out what it is. And since this was 5 pi over 7, by symmetry, that'll be 2 pi over 7. Okay. Yeah, and so the question, the math question, I'll answer that one first. Is would that be enough justification? I think so, yeah. Honestly, probably, I don't want to say things like this, but probably on a test, a question like this would be multiple choice or something like that, in which case, never mind. Yeah, that would be enough justification. Okay, Amelia asks, what's my favorite song? That's really tough. The first song that came to mind is Somewhere a Judge by Hop Along. I guess I'd rather do 50 duck-sized horses because I feel like I could take them out just by kicking. Okay, Arik wants to know the story behind my tattoo. It's my heart rate on 2 different days. This was one day where I failed a really important exam, and I was extremely depressed and frustrated, and I thought I was going to get kicked out of grad school. And then this was 6 months later after I spent like hundreds of hours studying and mentally preparing and dealing with my anxiety and stuff like that, and I eventually passed. So that was the day I passed it. That was the day I failed it. Important moment for me. Okay, I'll answer a few more and then we'll go back to math. If I wasn't a math teacher, what would I be doing? I have no clue. I'd be a pop music songwriter. That's my other career option. How much do I bench? This past week, I benched 215 with a pause. And that was after running the marathon on Sunday. So I didn't bench all quarter, ran the marathon on Sunday, and then a couple days later, I did 215. I don't know if there will be multiple choice on the exam, so I'm not sure. Okay, let's do some more math. I'll come back and answer more later. We've got priorities though. Let's do, oh, I know what I was going to do. Yeah. A Taylor polynomial question. Okay, so let f of x be 1 plus x minus x to the 4th. I have a couple questions. What is T4 of x centered at 0? How about T2 of x centered at 0? How about T4 of x centered at 1? And then lastly, how about T2 of x centered at 1? Okay. Now, these are all things that you could just sit down and compute. Okay, so really quickly, some other relevant questions. 32B next quarter, I'll be doing this. I'll be live streaming all discussion sections, all office hours. If you're taking 32B next quarter, anyone's welcome to E-C me, and I'll upload everything on this YouTube channel, so keep an eye on that. Marathon was good. It was hard. Workout routine, I'm still trying to figure that part out. I have no clue what we're going to do. Okay. What's the point here? These are all things that we could just sit down and compute. Like, how do you compute a Taylor polynomial? You just compute all the derivatives, plug stuff in, and go from there. And we could do that, but conceptually, some of these we can knock out pretty quickly. For example, T4 in part A, centered at 0. In words, what is that? T4 is the best degree 4 polynomial centered at 0, which approximates that. And the idea is, what's the best polynomial of degree 4 which approximates this? It's already a polynomial of degree 4. So itself, it is the best approximation of itself as a degree 4 polynomial. So without any computation, I could say forth. And again, if you don't believe me, you can just sit down and compute. But the point here is that you don't really need to, actually. So in part B, so this is T4 at 0, and then this will be T2 at 0. What is the best degree 2 polynomial centered at 0, which approximates this polynomial? Because this is a polynomial centered at 0 already, to get the best degree 2 approximation, we would just take all the terms of the polynomial up through degree 2. So let me write that over here, actually. So here, just take all terms up to degree 2 of the original. Because f is already a polynomial centered at 0. B, 1 plus x, that's the degree 0 and the degree 1 term. And then I also want to include the degree 0 term. Uh-oh. But what is the degree 2 term? What is the degree 2 term there? It's 0. There is no x squared. So that would be T2. And again, if you don't believe me, you can just sit down and compute. Okay. So T4 of x at 0, I could call that a Maclaurin polynomial. Yeah. It actually, in this specific case, is the Maclaurin series as well. It's a finite series, but it is the Maclaurin series. Yeah. Okay. Part C, what about T4 centered at 1? Okay. What is the best degree 4 polynomial centered anywhere which approximates this? It's still itself. So I claim that T4, and again, if you don't believe me, compute it, simplify everything, and you should get that. So that's a really good question. I keep saying that f of x is a polynomial centered at 0. A polynomial centered at a just has terms that look like x minus a to the n. That's what I mean by that. So since f already has, or f has terms that look like x minus 0, x minus 0 to the 4th, That's what I mean by centered at 0. That's a really good question. I should have explained that a little more. Okay. The most interesting one here to me is part D, which I'm hiding right now, is what is t2 of x centered at 1? Is it just the first two terms like we did in part B? The answer is no. Changing the center can screw you up. So let's check. And this last one, I will actually just straight up compute. We'll just use the Taylor polynomial formula. So T2 that we care about is going to be centered at 1. It'll be f of 1 plus f prime of 1 times x minus 1 plus f double prime of 1 times x minus 1 squared all over 2. So let's just compute this now. Get this out of the way. So f of 1 is 1 plus 1 minus 1 is 1. Okay. F prime of x is 1 minus 4x cubed. So f prime of 1, which is what I care about, is, and then f double prime of x is going to be negative 12 x squared. So f double prime of 1 is negative 12. So plug these numbers in there, and that'll give us T2. So T2 that we care about is, let's see, f of 1 was 1 plus negative 3 x minus 1 plus, and the point is that this is definitively not this, because it's going to have x squared terms. So the point here is that changing the center in general in these Taylor polynomial computations can change a lot. Yeah, so I didn't explain this very well. How do I know that T4 centered at 1 is also the same thing? Because when you have a degree, say 4 polynomial, and you start computing Taylor polynomials centered anywhere, so like let's say here's the polynomial and it's centered at 0, and then I start computing Taylor polynomials centered at 1, it turns out that like the first Taylor polynomial might be different, the second one might be different, the third one might be different, but as soon as you get to degree 4, everything locks into place and you get the same polynomial. Roughly, the series converges at 4 no matter where you are, once you get to degree 4. I wouldn't worry too much about this, to be honest. And like I said, if you don't believe me, you can just try it out. Just sit down and compute, and everything should work out. Like I said, to be honest, I wouldn't worry too much about this kind of thing, though. Okay, let's see. What questions did I skip? Pop music songwriter, that's what why did I want to get a PhD in math? Well, I really liked math in high school, so I decided to major in math. And then I was okay at it, so I just kept doing it. And then I was about to graduate, and I was like, what do I do now? And I thought, I guess I'll just keep doing math. So to be completely honest, it was a lot of momentum that got me here. Another real answer is that I found that I really like teaching, and that's ultimately what I want to do. How many jumping jacks does that translate into? Probably 1,000 at least, if I had to guess. Leslie asks where I'm from. I was born in Kansas, and I grew up in Ohio. So I have a really exciting background. How will I spend my quarantine? Making math videos. Probably that. Probably that's it. Okay, let's move on. Let's do integral. Whoops. I'll just erase this. Next integral I want to do is x plus 8 over x squared plus x minus 6. I think that's what I wanted to do. Yeah, let's try this. Okay. So I get this. I look at it and I start thinking about my options, the first of which is any obvious algebra or a simple U substitution. I don't think that'll work here. If there was any kind of substitution that would work, usually with this kind of thing, it would be the denominator. So we could just think in our heads, like if we called u x squared plus x minus 6, du would be something like 2x plus 1. And that doesn't match up so well with the numerator. So I don't think that'll work. Okay, so then what? Then I start thinking about chapter 8 techniques. We could integrate by parts, we could do some kind of trig nonsense, or we could do partial fractions. This feels like, and it's not necessarily partial fractions, but that's usually a good indication that that's the point of the question. So I look at this and I'm thinking maybe partial fractions, just because it's a rational function. So then if I decide that I want to do partial fractions, the main thing I have to consider is, can I factor the denominator more? Because if I can, I should. And in this case, I think we can. 3 and negative 2 would give negative 6, and then 3 minus 2 is 1. So I think this should factor as x plus 8 over, let's see, x, what did I say? Plus 3, x minus 2. Okay, so we factored things as much as possible. Then when we do partial fractions, all we're doing is we're saying, I just want to break this fraction up into simpler fractions. Last night, we had a scenario where we had an irreducible quadratic factor. It's a little simpler here. We have two linear factors, which means I want something over x plus 3, and then something over x minus 2. And then what goes on top? I don't know. That's what we have to figure out. Now, the thing to remember is that whatever you put on top, that's going to be an expression of degree 1 smaller than the degree of the bottom. The degree of the bottom here in both of these factors, sorry, let me say that more precisely. The degree on top will be 1 smaller than the degree of the factor on bottom. So since the degree of the factor here is 1, the thing that goes on top is going to be a degree 0 expression. A degree 0 thing is just a constant. So I'll put an unknown constant there. The same logic applies here. So I put another unknown constant. And all we have to do is just algebraically figure out what A and B are. The next thing you want to do from here is multiply by the denominator just to clear all the fractions, because fractions are annoying and it's easier to work with polynomials. So the next thing I'll do is I'll multiply through both sides by this. When I do that on the left, I'll just get x plus 8. And then on the right, when I multiply this term by this denominator, the x plus 3's cancel out, and that will leave me with a times x minus 2. Likewise, plus b times. Here, the x minus 2's cancel out, and I'm just left with an x plus 3. Okay. How's that so far? That looks good. And then the thing to keep in mind with partial fractions is that from here, if you have linear factors, or in other words, if you have degree 1 factors, the thing that you want to do is plug in the roots of those factors. You can do whatever you want, but this is usually the most effective strategy. So by that I mean one of our factors is x minus 2. The root of that factor, the thing that makes this 0, is 2. So what I would do is I would plug in x equals 2. We'll get an equation, and what's going to happen is when we do that, it'll tell us what b is. So when I plug in 2, I get 2 plus 8 is 10 equals 0 times a. So this whole thing is 0. That's why we plug this in. And then here I'm left with b times 5. And it looks like b has to be 2. Nice. Then I can plug in the other root here is negative 3, and that'll tell us what a is. If I plug in negative 3, I get negative 3 plus 8 is 5 equals, so I'm left with this equation, and then it looks like a is negative 1. Okay, so then we're all ready. Tells me that this integral that we care about is the antiderivative of a over x plus 3. A was negative 1. Answer down here again. Sorry about that. Antiderivative here, this is just going to be a log of absolute x plus 3. So I'll get negative log absolute x plus 3. Plus, likewise here, I'll pull the 2 out, and then I get log absolute x minus 2 plus c. And that'll do it. Okay. So there's a partial fractions integral. Nice. Cool. All right, moving on. What do I want to do next? Oops. Oh, I did that. I will. Let me get an interval of convergence problem out of the way. We should all be able to do that. So I did one last night. I'll do another one tonight. Let's find the interval of convergence of how about this? This will be my plan for the next couple one. Interval of convergence, and then we should probably do an error bound theorem problem as well. All right, find the interval of convergence of Let's do the sum from 0 to infinity of x to the 7n over 3n factorial. It's kind of weird looking, but we'll go. Given a problem like this, what do? Almost every time you want to start off with the ratio test. Sometimes the root test is a better idea if you have really ugly looking exponential expressions, but a factorial kind of immediately tells you that you should do the ratio test and nothing else. So I'll start off by using the ratio test. So first, apply the ratio test here. The ratio test would say take the limit of, in absolute value, the n plus first term. This will be x to the 7 times quantity n plus 1 over quantity 3 times n plus quantity 3n plus, sorry, I have no clue what I was saying. 3 quantity n plus 1 quantity factorial. Then I'll divide that by the nth term here. So this will be like 3n factorial over x to the 7n. That's the limit we have to compute. As usual, I group things that came from the same spot. So x to the 7n plus 7, when I distribute this, over x to the 7n. And then here I've got a 3n factorial over. Here I'll distribute the 3 onto the n plus 1 to get a 3n plus 3 quantity factorial. Okay. Now let's simplify this stuff. We'll have to be a little careful. So if you don't have linear factors in a partial fractions problem, usually the thing that I do is I compare coefficients. So I'll like look at the x squared coefficients or the constant coefficients and things like that to determine the specific example of that. You can click on the video about partial fractions I made, and I think I linked certain kinds of examples. You could pick like the quadratic factor example. Oh no. Unable to connect to chat. That's not good. Oh well. As long as you can still hear me, I guess that's what's important. But yeah, if you want, I do an example like that. And so the strategy that I usually use is comparing coefficients. Okay. Here, x to the 7n plus 7 over x to the 7n, 7n of these will cancel out on top, and that will leave me with x to the 7th. Whoops. Then we have to figure out how this stuff simplifies. So usually the game that you want to play here is I'll leave 3n factorial alone. And then I'll think about what 3n plus 3 factorial means. Well, this means start at 3n plus 3, multiply by the next smallest number, which in this case would be 3n plus 2, multiply by the next smallest number, which would be 3n, and from there on out, 3n minus 1, that's 3n factorial. So in this case, if we track how things simplify, the 3n factorials cancel out, and I'm left with 3 different terms in the denominator. okay? Take a limit as n goes to infinity, we get 0, right? Doesn't matter what x is, the limit's going to be 0 every single time. And since 0 is always less than 1, it doesn't matter what x is. That tells us that the interval of convergence is everything ever. So since 0 is less than 1, independent of x, by the ratio test, this series converges for all x. That is to say, the interval of convergence is the interval negative infinity to infinity. Done. Okay, that's an interval of convergence problem. Did you guys get my test chat message? It doesn't matter. Okay, moving on. I want to do an error-bound theorem, and then we'll do some more integrals, maybe. Okay. How about this? We could do a hardish error-bound theorem problem or an easier error-bound theorem problem. You can tell me what you want to do. How about that? I'm going to sit for like 10 seconds to rest. Although maybe no one's chat is working now. Or maybe no one can hear me. Who knows? Can anyone hear me, or can anyone chat anything? Maybe the chat feature died. No? Well, I'll do a hard error-bound theorem problem. How about that? Okay, I don't know. I guess I'll keep talking. Hopefully you guys can still hear me. Okay, so here's the next example I'll do. Let f of x be, let's do log of x. And I'll let Tn be the Taylor polynomial of log of x centered at 1. And I want to find an n such that, let's do log of 1.3 minus Tn of 1.3 is less than 1 over 10,000. Let's do that. Okay. So as usual, what's the point with these error-bound problems? Even if we don't quite understand the statement of the error-bound theorem, I read the problem and I recognize that I have to use it. So let me remind us what the statement of the error-bound problem is. Let's see. The error-bound theorem says, with this setup, the difference between f of b and Tn of b in absolute value is less than or equal to some magic number k times the absolute value of b minus a to the n plus 1 all over n plus 1 factorial. Now, this doesn't quite make sense because I haven't specified what k is, so I have to tell you what k is, where k is an upper bound for the absolute value of the n plus first derivative on the interval a to b. So it's a mouthful, as usual. The error-bound theorem just says that the difference between the function and the polynomial is going to be smaller than something, and that something depends on the n plus first derivative. And what we need to do is we need to find an n so that that something is really small. Hold on, checking my email really quick. Okay, thanks. So the first step in all of these problems, in my opinion, is just to spit up the error-bound theorem and see what it tells you. So I would say by the error-bound theorem, what can I say about this quantity that I care about? Log of 1.3 minus Tn of 1.3 in absolute value is going to be less than some number k, which we'll find in a second, times what? B minus a. In our case, b is 1.3, and a, excuse me, is 1. And again, k, the number that we'll have to do a lot of work to find, is an upper bound for the n plus first derivative on the interval, in our case, from 1 to 1.3. Okay. Live streaming, I feel a little nervous about doing that. Because no one's talking. Do you want to try? Okay, yeah, try it. All right, well, I'll keep going until then. Okay, so as usual, to figure out k, we're going to need to understand the n plus first derivative here. This is a scenario where we'll just have to sit down and compute the n plus first derivative, and there's no good way around that. So next, we'll compute the n plus first derivative of f of x. Did you try something?
They asked what are they trying?
Can you see chat?
Yeah.
I can't see anything. Okay. I'm going to, I don't know what's going to happen. I'm going to refresh my page. If that ends the stream, then I'll start it up immediately again. So we'll see what happens. I wish I knew how this stuff worked. Okay, I'm refreshing. Stay tuned. Changes I made may not be saved.